Hello again and welcome to our lesson number 3 of Chemistry 12, Unit 1, Structure and Properties of Matter. Today's lesson is going to cover the concept of quantum numbers. Let's examine quantum numbers in detail. Quantum numbers describe aspects about the location of electrons. Scientists cannot determine the actual path of an electron, but rather the probability of finding the electron in a region. This is known as the Heisenberg uncertainty principle. Because particles are moving, therefore, we can only have an estimate of the high probability of finding an electron. There are 4 quantum numbers to describe the electron that we study in high school. These are, number 1, the principal quantum number abbreviated with the letter N. That represents the main energy level of an electron and is referred as the shells or orbits in previous diagrams in the Bohr-Rutherford diagram. N denotes the probable distance of the electron from the nucleus, and N ranges from n-1 to infinity. But N can never be equal to 0. The diagram on the right-hand side is similar to a Bohr-Rutherford diagram with the rings representing the energy levels N1, N2, N3, and 4. If an electron is found at N4, it's farther away from the nucleus than if it's found at N1. N1 has the lowest energy. So the energy levels increase as the number of N increases. The energy levels are like unequal steps on a staircase. The maximum value the N can have for an electron in an atom is equal to the period the atom is found on the periodic table. So you would have to find a specific element in the periodic table, and depending on the location on which row or period, that would define the maximum value of N. The number of electrons that can fit in an orbit or energy level is 2n to the second power. That's the formula. The second quantum number that we study is the secondary quantum number abbreviated with the italic letter L, and that represents the shape of the orbital or the region in space where we might find an electron. That's known as orbitals. The secondary quantum number is also known as the angular momentum in many textbooks. It describes the shape, as I mentioned before, and its values range from 0 to n-1. These values are obtained from solving Schrodinger's equations for orbitals, for a wave. The L is also known as energy sublevels or subshells. Let's examine the shape of those orbitals. So the very first shape is known as the S shape or S sharp or a sphere. Thus, an S orbital is represented with the value L equals 0, has a spherical shape, and is centered around the origins of the 3 axes, as shown on the figure on the right-hand side. It's centered on the X, Y, and Z. The second shape of the orbital is known as the p orbital or principal, and that has the shape of a dumbbell. As you see over here, these are 3 dumbbells that are aligned to the 3 axes in the 3 diagram, aligned to the X, the Y, and the Z. So therefore, there are 3 different p orbitals at energy levels, starting with energy level 2. Same type of orbitals with the same amount of energy are called degenerate orbitals. So the px, py, and pz are known as degenerate orbitals because they have the same amount of energy. The third shape is called the diffuse orbital shape, or D. This one is a bit more complicated with the 5 d orbitals. You see there are 5 d orbitals or 5 shapes, and they're much easier to remember if you think of them as a dumbbell with a donut or 2 dumbbells, and they align accordingly to this diagram shown here. So there are 5 d orbitals. Remember, each orbital takes 2 electrons. So the d orbital takes up to 10 electrons. The next orbital shape is called the fundamental, or the F. It's rather complicated. It's abbreviated with the value L equals 3. and that's for the orbital shape F. The orientations are shown over here. There's 1, 2, 3, 4, 5, 6, 7 orientations, which corresponds to these values when ml equals -3 to -2, -1, 0, +1, +2, +3. If we have 7 orientations, we know that each orbital takes 2 electrons, so the f orbital altogether, all the f orbitals can hold up to 14 electrons. The possible values of L in any given energy level are 0 to n-1, and the values of L can be equated to the shape of the orbital. That is, if we talk about L equals 0, we're talking about an S or a sphere orbital. If we say L equals 2, then we're referring to a D orbital. If we say L equals 1, we're referring to a P or dumbbell orbital. And if we say L equals 3, we're referring to the F or fundamental orbital. The third quantum number that describes the electron is known as the magnetic quantum number, and that describes the direction or the orientation of the orbital in 3D. It refers, in other words, to the alignment of the orbitals with reference to the 3 axes in a 3D diagram. For simplicity, I've chosen the p orbital shown here, the dumbbell. So a dumbbell can be aligned to the x, y, or z, and they're known as px, py, pz. The magnetic quantum number has possible values, and those values range from -L to +L, including the 0. And if L equals 1, therefore ml is going to be -1, 0, 2, +1. And there will be 3 orbitals that have the same energy. Remember, these are called degenerate orbitals. The total number of orbitals for any energy level can be calculated using the formula n to the second power. And each orbital can hold 2 electrons, as I've been mentioning through the presentation. The fourth quantum number is called the spin quantum number. This number has been encountered with observations that scientists made about emission lines of elements in magnetic fields and the 2 types of magnetism. So if you remember, you studied magnetism a little bit in grade 9. You studied maybe the most important, common one is ferromagnetism that occurs in compounds containing iron, cobalt, or nickel, and is due to the magnetism of a collection of atoms. The second type of magnetism is known paramagnetism. It's relatively weaker to attraction to a strong magnet, and it refers to the magnetism of individual atoms. So that can be explained. The paramagnetism could not be explained until Wolfram Pauli suggests that each electron is spin on its axis. So an electron is a tiny, tiny particle with a charge. So particles with charge exert the ability to form an electromagnetic field. As shown over here, this will be the electromagnetic field. So the opportunity of this electron, when they in close proximity to another electron, they would affect the way they spin, but via the electromagnetic field. So they can spin in a clockwise direction shown on the bottom, or a counterclockwise. In a clockwise direction, yes, shown on the bottom, or counterclockwise direction shown on the top. So they refer as the +half or -half values. So each electron is spin as either clockwise or counterclockwise. So let's summarize the 4 quantum numbers in the lesson. The principal, abbreviated with the symbol n, and the possible values 1, 2, so forth to infinity, specifies the shell and indicates or represents the size and energy of the electron of the orbital. The orbital angular momentum quantum number is represented with the symbol L, and the values are 0, 1 to n-1. Specify the subshell. The values of L are represented with the numbers 0, 1, 2, 3, 4 that represent the shape of the orbital SPDF. And again, this number represents the shape of the orbital. The third quantum number is called the magnetic quantum number, represented with the letter ML. The values are L to L-1, including 0, and it specifies the orbitals of subshells. That indicates the orientation of those orbitals with reference to a 3D diagram. And the last the fourth quantum number is called the spin quantum number, represented with ms. The values are plus half and minus half, and specify the spin state, and in the case the direction of the spin, either clockwise or counterclockwise. So in the next lessons, we're going to apply these quantum numbers to write quantum numbers for any given electron in any given atom. Thank you.